Hi, I am going to work on question 1 from homework or lab project chapter 4. And in this case, I'm looking at a problem where I have two variables. One is called the salary paid to a team of baseball players, and the other variable is called wins. And clearly, this student understood the difference between explanatory variable and response variable. So whenever we're associating two different variables, we associate one, or we assign one the role of predictor. And we use the horizontal axis in a coordinate system in a Cartesian plane. We use the horizontal axis to map what's going on with this predictor variable, which in this case is salary. And wins goes on the vertical axis, and we call this variable the predicted variable. And as you can see by what's given here in this problem, there's a model that's already been computed. And so in the model, we are using wins to be the variable that we're trying to predict. And we're going to predict them via a regression model that's already been computed. Based on millions of dollars of salary. We're going to use the color blue to map these predictions in the Cartesian plane of x and y. So we have a line like this that represents predicted wins. Actual wins are going to be in black and white, predicted wins in blue. And salary in millions of dollars is the variable in the x-axis. In blue here, we have this model that we call the regression model. So this is called a linear regression model. In this case, we're going to be predicting this y-intercept is telling you what you expect the wins to be at a salary of 0 millions, which would make kind of no sense because nobody would play professional baseball for free. The whole point of playing professional baseball is to earn a living and a salary by being a professional in the sport. So that point doesn't make sense from the perspective of predicting a team that pays 0 in salaries. What makes more sense is to interpret the 6297 as the number of wins regardless of salary, regardless of what you pay the baseball players. How many wins can you expect the team to earn? Then we are told also that there's this average, and this average is for 81 wins, and that's an actual data point. So I'm going to put it in black and white of where that heart is located. Okay, and so this model, this blue line here, will at some point intersect this purple line. We'll put a star at that location. And from there, we can measure what is really going on in a team that earns 81 wins. And we could look at what actual teams are, how actual teams are varying from 81 wins in the wide dimension, as well as how much they vary in the salaries they pay players. In other words, there will be some teams that you pay a lot of money to that don't make 81 wins, and you're wondering what's wrong with them because these players are making too much money to be failing. And then there are teams that are like super surprising, low salary and high winners, and you'll be wondering what makes these teams great. There's a statistic called the R-square, and what the R-square statistic measures is how well X explains Y, how well salaries explain wins. And it does this in percentage terms. Okay. So in this case, they tell us that the R-square is 38.8%, which means that variations in salary only explain 38.8% of all variation in wins. So what that means is that salary is not a very good indicator of or predictor for how well a team will do. If that were the case, the Yankees would always win the World Series, but as we can tell, that doesn't happen even very often. So clearly the amount of money you pay ball players is a function of how entertaining they are in many ways and how good they are, but that doesn't necessarily mean that as a team they will gel and win a World Series all the time, or even a lot, or even often. Another statistic that we see in this problem is one called the standard deviation of the residuals. And what this measures, this is a measure of spread because it's a standard deviation. It measures how much the actual XY data points vary from the linear path. Okay, so that's the job of the variable of the residual standard deviation or regression error standard deviation. We were told in this problem that this particular measure of standard deviation is 9.5 games, give or take, plus or minus. And so what we are seeing in the data according to this is a spread that spans a give of 2 times the standard error. So that would be 19 games above the usual. And also 19 games below the usual. So there's a lot of error in the actual data from this blue regression line. You're going to see a scatter plot that has data that's very scattered around the regression line for this problem. Okay. So if a team spent 95 million in salaries and won 81 games, the predicted number of wins here would be 62.97 plus 0.121 times 81, which is the number of won games. And that would be 74 and a half, more or less. 62.97 plus 0.121 times the amount of money paid, which is $95 million. That would give you 74 and a half. Since they actually won 81 games, the team that spent 95 million won 81 games, they won more games than predicted. So they did better than predicted. A residual is always the actual minus the predicted. So in this case, since they won more games than predicted, their residual will be positive. And in this case, it's positive 6.5 games. And because this model has a low R squared, it only predicts 38.8% of wins. This model is not very useful because the R squared is low. And I cannot predict games very accurately because I'm going to be off the mark by 2 standard deviations or 19 games. Since the average team wins 81 games, 2 deviations from that is as high as 100, as low as 62. The 62 comes from subtracting 2 deviations from 81. And adding 2 deviations from 81. So we're going to be adding 19 points to 81 to get 100 on the top. And we're going to be subtracting 19 points from 81 to get 62. And as you can see, that range of 62 to 100 is enormous. So most teams fall in this interval. I hope this video was useful in completing question 1 of your lab work. Thanks.